The cosmos is expanding faster than we can comprehend, stretching the fabric of space itself. This incredible acceleration is driven by a mysterious force called dark energy, an enigma that makes up most of our universe yet completely defies explanation. Picture the universe like a runaway balloon, inflating at a rate that is not just steady but constantly increasing, and no one knows who is blowing the air into it. Over the next 25 mysteries, we will journey into the heart of this cosmic puzzle, from the phantom energy that could tear reality apart to the shocking possibility that our entire understanding of gravity is wrong. By the end, you will grasp the fundamental questions that keep cosmologists awake at night and the revolutionary answers that might be just over the horizon. How can nothing, the empty vacuum of space, possess an energy so powerful it dictates the fate of everything? What does a force that isolates galaxies forever mean for our own distant future? Which of these cosmic secrets do you think will be the first to fall? This first mystery strikes at the very heart of physics. The cosmological constant problem is often called the worst theoretical prediction in the entire history of science. It begins with a simple, profound question. What is the energy of empty space? According to our best theories of quantum mechanics, the vacuum is not truly empty. It is a seething, bubbling foam of virtual particles popping in and out of existence. This quantum frenzy should endow every tiny volume of nothingness with a colossal amount of energy, a vacuum energy that should act as a powerful repulsive force. This is where the math goes completely off the rails. When physicists calculate this predicted vacuum energy, the number they get is wrong. Not just a little wrong, but wrong by a factor of 1 followed by 120 zeros. To grasp the sheer insanity of this number, consider that the total number of atoms in the entire observable universe is only around 1 followed by 80 zeros. Our prediction for the energy of nothing is a trillion times larger than the amount of energy in all the something that exists. This is not a small rounding error. It is a screaming void in our understanding, a fundamental disconnect between the world of the very small and the very large. This staggering mismatch forces us to confront a terrifying possibility. Either our theory of quantum mechanics is profoundly incomplete, or our theory of gravity, Einstein's general relativity, is wrong. Or perhaps both are merely approximations of a deeper, hidden truth we have yet to uncover. This leads to another haunting question known as the cosmic coincidence. The observed strength of dark energy is incredibly weak, yet it is not zero. And we happen to live at the precise cosmic moment, just a few billion years after the Big Bang, when the density of dark energy has become comparable to the density of matter in the universe. Why now? For nearly the entire history of the cosmos, matter was dominant, and now, for nearly all of its infinite future, dark energy will reign supreme. Our existence seems to be perfectly timed to witness this delicate, fleeting balance. Is this just a lucky accident, or is it a crucial clue pointing toward a deeper law of nature we have yet to decipher? This staggering mismatch forces us to ask if we are even asking the right question. Perhaps dark energy is not a simple, immutable feature of space, but something that evolves. This brings us to the second profound mystery. Is the strength of dark energy truly constant, or has it changed over the vast history of the cosmos? The answer to this question is quantified by a value scientists call the equation of state parameter. In simple terms, this is just a number that tells us how the pressure of dark energy relates to its energy density. For a pure cosmological constant, the simplest form of dark energy, this number is exactly -1. It never wavers, but what if it does? Measuring this single number with extreme precision has become one of the most important goals in all of modern cosmology. Massive collaborations like the Dark Energy Survey have spent years meticulously mapping millions of galaxies. tracking their distances and how fast they are moving away from us. They are essentially constructing a cosmic history book, chapter by chapter, to see if the push of dark energy has been the same in every era. The future Nancy Grace Roman Space Telescope is designed to take this search to a whole new level, peering deeper into the past than ever before. If these powerful observatories find that the equation of state parameter is not exactly -1, if it has deviated even slightly over billions of years, then everything changes. A changing dark energy would mean it is not a static energy of the vacuum, but a dynamic force. Scientists have a name for this possibility: quintessence. Imagine quintessence not as a constant, but as a cosmic field that permeates all of space, a field that can slowly shift and evolve over time. Its strength could have been different in the early universe and could continue to change in the future. This would be a revolution on par with the discovery of dark energy itself. It would mean the fate of the universe is not sealed by a simple number, but is governed by a new, fundamental ingredient of reality, a fifth force beyond the four we know. This would shatter the standard model of particle physics and open the door to an entirely new understanding of the cosmos. The quest to measure this one number is a race to determine if we live in a simple, if puzzling, universe or in a complex and dynamically evolving one. A dynamic dark energy, a quintessence field, is strange enough, but the equation of state parameter could theoretically plunge to values far more extreme than -1. This is the territory of the third and perhaps most unsettling mystery, the phantom energy menace. Phantom energy is not just a stronger form of dark energy, it is something conceptually different and far more destructive. Its defining characteristic is an equation of state less than -1, meaning its repulsive power would not just remain constant, but would intensify as the universe expands. This creates a terrifying feedback loop with truly apocalyptic consequences. As phantom energy drives the expansion faster, space stretches, which in turn makes the phantom energy even more powerful, which drives expansion even faster in a cycle that has no natural limit. The end result of this runaway process is a cosmic doomsday scenario known as the Big Rip. Imagine the force of dark energy, which today is gently pushing galaxies apart, growing exponentially stronger over billions of years. First, it would overcome the gravitational glue holding clusters of galaxies together. These vast cities of stars would be flung into the ever-expanding emptiness, isolated forever. Then, as the force continues to amplify, it would set its sights on individual galaxies. The Milky Way itself would be shredded, its stars scattered like dust in a hurricane. The horror would not stop there. In the final moments, perhaps in the last hour before the end, the repulsive force would become stronger than the forces holding solar systems together. Planets would be ripped from their suns. Then it would target planets and stars directly, tearing them apart against their own gravity. In the last fleeting seconds, the phantom energy would exceed the very nuclear forces that bind atoms together. Every molecule, every atom, every proton and neutron in the universe would be violently torn asunder. The entire cosmos would dissolve into a thin, cold mist of fundamental particles, unable to ever interact again. The universe would not end with a crunch or a fade, but with a catastrophic and absolute disintegration of spacetime itself. The search for phantom energy is therefore a race to measure the equation of state with a precision we have never before achieved. Astronomers are using the most powerful telescopes to observe the most distant supernovas and the large-scale structure of the universe, looking for any tiny deviation in the expansion history that hints at this terrifying potential. Finding evidence for phantom energy would be one of the most profound and frightening discoveries in human history. It would not only reveal the ultimate fate of all existence, but would also force us to completely rewrite our understanding of fundamental physics, proving that the vacuum of space harbors a force of destruction beyond our wildest nightmares. This growing phantom energy threat forces us to look more closely at our measurements of cosmic expansion, and it is here we stumble into a full-blown crisis in cosmology. The fourth great mystery is known as the Hubble Tension. At its heart is a simple, stubborn question: how fast is the universe expanding right now? You would think we could just measure it and get a single number, but we get two very different answers depending on whether we look at the ancient universe or the modern one. The first method uses the afterglow of the Big Bang itself, the cosmic microwave background. By studying the tiny fluctuations in this ancient light, we can calculate how fast the infant universe was expanding and then use our model of cosmology to predict what the expansion rate should be today. This is like calculating how fast a teenager will be running in their 40s based on a childhood photograph and a model of human growth. The other method looks at the local, contemporary universe. Astronomers observe stars called Cepheid variables and type 1 as supernovas in nearby galaxies. These are known as standard candles because their intrinsic brightness is well understood, allowing for a direct measurement of their distance and how fast they are moving away from us. This is like using a radar gun to measure the runner's speed today. The problem is, these two methods do not agree. The local measurement gives a faster expansion rate than the prediction from the early universe. The discrepancy is not large, only a few percent, but its statistical significance is overwhelming. This is not a simple error bar overlap. It is a persistent, glaring mismatch that has survived over a decade of increasingly precise observations. So what does this mean? Either there is a hidden, unknown systematic error in one of our most trusted measurement techniques, something we have overlooked for years, or our standard model of cosmology, the very foundation of modern physics, is missing a crucial ingredient. One of the most exciting proposals is the existence of early dark energy. This is not the dark energy we see today, but a new form of energy that may have existed for a brief period in the universe's first few 100,000 years. This early dark energy would have provided an extra burst of repulsion, subtly altering the expansion history just after the Big Bang. It would have changed the conditions recorded in the cosmic microwave background, meaning that when we use that ancient light to predict today's expansion rate, our prediction would be wrong because our model of the past was incomplete. The Hubble tension is more than a scientific disagreement. It is a direct challenge to our understanding of cosmic history. It forces us to ask if the laws of physics were slightly different in the primordial universe, or if dark energy itself is far more complex and dynamic than we ever imagined. Solving this puzzle could require a revolution as profound as the discovery of dark energy itself, rewriting the first chapters of our cosmic story. This brief window of balance we find ourselves in is the fifth and perhaps most personally resonant mystery, the cosmic coincidence problem. Why does the energy density of dark energy so closely match the density of all the matter in the universe right now, in our specific cosmic era? For nearly 14 billion years, the universe was dominated by matter. Galaxies formed, stars ignited, and planets coalesced under the steady, pulling hand of gravity. Dark energy, if it existed at all, was a whisper in the background, completely negligible. And in the far, far future, dark energy will be the undisputed ruler. It will dilute matter to near nothingness, leaving galaxies isolated and the cosmos a vast, expanding emptiness. Our present moment is a fleeting sliver of time, a blink in the eye of the cosmos, where these two titanic forces are in a near-perfect standoff. The odds of living in this precise transitional epoch are astronomically small. It is as if we walked into a library containing every possible history of the universe, and we picked up the one book where the chapter on balance happens to fall open on the very page we exist. This profound unlikeliness demands an explanation. One provocative answer is the anthropic principle. This idea suggests that the universe's fundamental constants, including the strength of dark energy, are not random. They must be compatible with the existence of conscious life to be observed. In a multiverse, a vast collection of universes, each with different physical laws and constants, we inevitably find ourselves in one of the rare universes where conditions are just right for life to emerge. In most universes, dark energy is either too strong, ripping apart proto-galaxies before they can form, or too weak, causing the universe to collapse back on itself long before life can appear. We are here because this is one of the very few universes that allows us to be here. Another compelling theory is that dark energy and matter are not independent. They could be coupled, interacting with each other in a way that naturally drives their energy densities to converge at a certain point in cosmic history. This would not be a coincidence at all, but the result of a hidden law of physics, a deep connection between the stuff we are made of and the dark energy that fills the void. This coupling could mean that as the universe evolves, the decay or evolution of matter fields directly influences the strength of dark energy, orchestrating this brief period of balance. The search for this coupling is a search for a more unified cosmos, one where the two dominant components of reality are in a silent, dynamic conversation. Are we the beneficiaries of a colossal cosmic accident? Or does our very presence point to a deeper, more connected universe where the stage was set for observers to arise? But what if the acceleration we measure is not a fundamental property of the entire cosmos, but a local trick of the light? This is the startling premise of the sixth mystery, the void hypothesis. It challenges one of the most sacred principles in cosmology, the cosmological principle, which states that on the largest scales, the universe is homogeneous and isotropic. This means it should look roughly the same in every direction, a uniform cosmic soup. The void hypothesis dares to suggest we might be living in a special place, a gigantic cosmic bubble that is significantly emptier than the average universe. Imagine our entire observable universe, out to billions of light years, sitting inside a colossal underdensity, a vast spherical region where the density of galaxies and matter is lower than it is elsewhere. How would this affect our view? In a denser region of space, the gravitational pull of all that matter would slow the expansion of the universe more effectively. Our local, emptier void would have less gravity to fight against, so the space within our bubble would expand faster than the cosmic average. When we look out from our relatively empty home and see distant galaxies receding at an accelerating rate, we might simply be witnessing the natural consequence of living in an underdense region, not evidence of a mysterious dark energy. It is like being in a valley and misinterpreting the local downhill slope as evidence that the entire world is tilting. This idea is profoundly appealing because it offers an escape from the perplexing reality of dark energy. It replaces a mysterious, unknown force with a simple, if enormous, feature of the cosmic geography. The problem is, the evidence for large-scale uniformity is overwhelming. The strongest counter-argument comes from the cosmic microwave background, the ancient light from the Big Bang. This radiation is incredibly isotropic, meaning it has the same temperature in every direction to within 1 part in 100,000. If we were living in the center of a giant void large enough to explain the apparent acceleration, that void would have to be so immense that it would leave a distinct cold spot in the cosmic microwave background, a giant shadow that we simply do not see. The cosmic microwave background shows us a universe that was remarkably smooth and uniform in its infancy, making it incredibly difficult to explain how a void of the required size could have formed and survived to the present day. So we are left with a dramatic standoff. On one side, a simple and elegant alternative to dark energy. On the other, the pristine image of a uniform young universe. Resolving this tension pushes our observations to the limit. Astronomers are now meticulously mapping the cosmos in 3 dimensions, looking for any evidence of a gigantic structure that could be our cosmic neighborhood. They are measuring the velocities of millions of galaxies to see if we are in a region where everything is flowing outward, away from a denser surrounding shell. The void hypothesis, while a long shot, forces us to question our most basic assumptions about our place in the cosmos. Are we truly in a generic region of a uniform universe, or could we be living in a special cosmic backwater, fooled by our local environment into believing the entire fabric of reality is being pushed apart by an unseen energy? This fundamental debate forces us to question the very laws that govern the cosmos. Is the universe's acceleration driven by a new, exotic substance called dark energy, or is it a glaring sign that our theory of gravity itself is wrong? Einstein's general relativity has passed every test with flying colors for over a century, from predicting the bending of starlight to explaining the orbit of Mercury. But all its tests have been within the relatively strong gravitational fields of galaxies and stars. On the vast, cosmic scales where the fabric of space itself stretches between galaxy clusters, could this magnificent theory finally be breaking down? The alternative is not to add a mysterious energy, but to rewrite the rules of gravity. One of the most prominent ideas is known as modified Newtonian dynamics, or MN. It was originally proposed to solve a different mystery, the fact that galaxies rotate too fast for the amount of visible matter they contain. MN suggests that gravity does not fade away as quickly as Newton or Einstein predicted in regions of extremely weak acceleration, like the outer edges of galaxies. This would explain the galaxy rotation problem without needing to invoke vast halos of invisible dark matter. But to tackle cosmic acceleration, man needed a relativistic upgrade, a full theory that could compete with general relativity. This led to theories like tensor vector scalar gravity, or TVS. In these frameworks, the accelerated expansion isn't a push from dark energy, but a pull. It is a natural consequence of the modified laws of gravity on the largest scales, where the gentle tug between distant galaxy clusters behaves differently than we thought. So how do we possibly choose between these two radically different explanations? The key lies in watching how the universe's structure grows over time. Imagine planting seeds in two different types of soil. In one, you add a special fertilizer that repels the seeds, pushing them apart as they grow. In the other, you change the soil's composition so that the roots simply do not intertwine as expected. The final pattern of plants will look different in each case. In our universe, the seeds are the tiny fluctuations in density from the Big Bang. Over billions of years, gravity pulls matter together, causing these seeds to grow into the vast cosmic web of galaxies and clusters we see today. If dark energy is a repulsive fluid, it acts as a sort of cosmic anti-gravity. It makes it harder for matter to clump together. It suppresses the growth of these large-scale structures. If we instead have a modified theory of gravity, the growth of structure would follow a different set of rules. The pull between matter might be stronger or weaker depending on the scale, leading to a different pattern in the cosmic web. Astronomers are now mapping the universe in 3 dimensions and across cosmic time, measuring the rate at which clusters of galaxies form and grow. They are looking for the subtle fingerprint that distinguishes a universe filled with a mysterious repulsive energy from one where the laws of gravity themselves are an illusion. The answer will determine the future of physics. Do we live in a universe dominated by a strange, dark component? Or have we been misreading the fundamental force that shapes reality from the very beginning? Our ultimate destiny hinges entirely on the true identity of this phantom pushing the cosmos apart. 3 vastly different endings await the universe, each dictated by the subtle behavior of dark energy. The first and currently most favored scenario is the heat death, also known as the Big Freeze. This future assumes dark energy is a true cosmological constant, forever unchanging. In this slow, cold finale, the acceleration continues at its current steady pace. Galaxies will be pushed ever farther apart, their light eventually fading from view. Star formation will cease as the raw material for new suns is locked away in isolated island universes. Over trillions upon trillions of years, the last stars will flicker out, leaving behind a cosmos of black holes, cold neutron stars, and dead planets. Even these remnants will not last. Through a process known as Hawking radiation, black holes will slowly evaporate over almost unimaginable timescales. The universe will approach a state of absolute equilibrium, a dark, dilute, and frigid sea where the temperature everywhere nears absolute zero. No energy gradients will remain, no work can be done, and no complex processes can ever occur again. It is a quiet, eternal fade to black. The second possibility is far more violent and immediate. If dark energy is phantom energy with an equation of state less than -1, then the universe is headed for a big rip. This is not a slow decay but a catastrophic disintegration. The repulsive force grows without bound, eventually overwhelming every force that holds reality together. First, galaxy clusters are torn apart, then individual galaxies. In the final moments, stars, planets, and even atoms themselves are ripped to shreds by the escalating pressure of space itself. The cosmos ends not with a whimper but with a scream as the very fabric of space-time is torn asunder. The third and most cyclical possibility is the Big Crunch. This requires that dark energy is not constant but is instead a form of quintessence that decays over time. If its repulsive power weakens and eventually becomes attractive, the expansion of the universe could slow, halt, and then reverse. Galaxies would begin rushing back toward each other, pulled by a resurgent gravity. The temperature of the cosmos would rise as space is compressed, eventually melting all structure back into a seething, hot plasma. This could culminate in a spectacular collapse back into a singularity, a mirror image of the Big Bang. Some theories even suggest this singularity could then rebound, triggering a new Big Bang and an entirely new universe, giving rise to an endless cycle of cosmic death and rebirth. These are not just abstract fates, they are the ultimate consequences of the mystery we are trying to solve today. Does our story end in eternal silence, violent dissolution, or a fiery rebirth? The answer is written in the invisible, enigmatic nature of dark energy, waiting for us to finally read it. Our universe might be fundamentally impossible. This is the startling conclusion we face when we pit our successful model of dark energy against a set of ideas from string theory known as the swampland conjectures. These are not conjectures about swamps, of course, but a powerful and provocative framework for distinguishing consistent theories of quantum gravity from those that are doomed to be inconsistent. Think of it as a cosmic sorting mechanism. On one side lies the lush landscape of viable theories, theories that could potentially describe a real universe like our own. On the other side lies the swampland, a murky bog of theories that look promising on paper but contain fatal, internal contradictions that make them impossible in reality. The ultimate goal of physics is to find a single theory that unifies the large-scale laws of gravity with the small-scale laws of quantum mechanics, a theory of everything. The swampland conjectures attempt to draw a map toward that holy grail by defining the rules any such theory must obey. And here is where we collide with a profound mystery. Our simplest and most successful model for dark energy, the cosmological constant, appears to break one of the most important of these rules. This rule suggests that the vacuum energy, the energy of empty space that drives cosmic acceleration, cannot be a fixed, unchanging constant like our cosmological constant. Instead, for a theory to be consistent, this energy must be dynamic. It must be able to change over time or across space. Our observed universe, with its tiny but stubbornly constant dark energy, seems to be sitting squarely in the swampland. This creates an unbearable tension. On one hand, we have our cosmological model, which fits a mountain of observational data with a simple, constant dark energy. On the other, we have our most advanced theoretical framework suggesting that such a universe is mathematically incoherent. Are we, and everything we see, living in a universe that should not logically exist? This is not a minor philosophical puzzle. It is a direct confrontation between what we observe and what we believe must be fundamentally true about reality. One compelling way out is if dark energy is not a constant after all, but a form of quintessence, a dynamic field that is slowly evolving. This would immediately rescue us from the swampland, aligning our cosmos with the conjectured laws of quantum gravity. The hunt for any tiny change in the strength of dark energy, which we discussed earlier, is therefore not just a search for a new particle or field. It is a search for our universe's very consistency, a quest to see if we reside in the secure landscape or are lost in an impossible swamp. This mystery forces us to ask if the ultimate laws of physics are flexible enough to accommodate the strange universe we see, or if we are on the verge of a revolution that will reveal our current model as a beautiful but ultimately flawed illusion. This silent conversation between darkness and darkness leads us to a 10th, deeply intriguing mystery. What if the two great unknowns of our cosmos are not strangers, but are in constant, hidden communication? We have been treating dark matter and dark energy as separate entities, one pulling things together with gravity, the other pushing them apart. But what if they are linked, two sides of the same enigmatic coin? This idea of an interaction could solve one of our most perplexing puzzles, the cosmic coincidence. Why do their energy densities match so perfectly in our present era? If dark energy and dark matter are coupled, their fates could be intertwined. Imagine them as two vast reservoirs of energy connected by a hidden pipe. As the universe expands and dark matter dilutes, its decreasing density could be subtly feeding the strength of dark energy, or vice versa. This dynamic link would naturally cause their energy densities to track each other over cosmic time, making the balance we see today not a freak accident, but an inevitable outcome of a fundamental relationship. It would mean the universe is far more connected than we ever realized. Proving this requires listening in on their cosmic dialogue. Astronomers are turning the universe itself into a giant laboratory, watching for the telltale signs of this interaction. The most promising method is to observe the growth of the largest structures in existence, galaxy clusters. Dark matter's gravity is the primary architect of these cosmic cities, pulling matter together over billions of years. If dark energy is interacting with dark matter, siphoning away its influence or changing its behavior, it would leave a distinct fingerprint on this growth. It would alter the rate at which clusters form and how many of them reach a certain size and mass at different points in cosmic history. By meticulously counting clusters across the universe and measuring their masses, we can see if the story of structure formation matches a model where the two dark components are independent, or one where they are in a silent, steady exchange. Another signature lies in the subtle warping of light from distant galaxies, an effect called weak gravitational lensing. This bending is caused by the gravitational pull of all the matter, both light and dark, along the line of sight. An interaction between dark energy and dark matter would subtly change how mass is distributed through space, imprinting a unique pattern on this cosmic lensing map. Finding this pattern would be like hearing the faint echo of a conversation happening in a dark room, revealing a connection that defines the very fate of the cosmos. The hunt for this interaction is more than just solving a coincidence. It is a search for a unified dark sector, a single theoretical framework that explains both of the universe's dominant yet invisible forces. Uncovering this link would be a revolution, revealing that the darkness is not a simple emptiness, but a complex and dynamic realm governed by its own hidden laws. This inability to directly witness dark energy stands as its most profound and frustrating challenge. We are surrounded by its effects, watching it sculpt the entire cosmos, yet the force itself remains utterly intangible. This is the 11th great mystery, the monumental challenge of direct detection. For all other fundamental components of our universe, we have a path, however difficult, toward direct confirmation. We built particle colliders to smash protons and reveal the quark gluon plasma. We constructed vast underground tanks to catch the rare flash of a neutrino, and we have even heard the ripples in spacetime from colliding black holes. With dark energy, we have nothing of the sort. Its presence is a ghostly influence felt only through the grandest of all possible scales, the stretching of spacetime itself. The reason for this elusiveness lies in its theoretical nature. If dark energy is indeed the energy of the vacuum, a property of empty space itself, then it is everywhere perfectly uniform and unchanging. It exerts no local push or pull that we can measure against a background because it is the background. Trying to detect it directly is like a single fish trying to detect the water in which it swims. There is no contrast, no localized source to pinpoint. Even the most promising alternative, a dynamical quintessence field, would be incredibly weak and uniform, its subtle variations lost in the noisy hum of the quantum world. This has not stopped scientists from dreaming of a breakthrough. The hunt is on for any minuscule signature that could bring dark energy into the laboratory. One frontier approach uses the most precise timekeeping devices ever created, atomic clocks of staggering accuracy. The theory is simple yet profound. If the strength of dark energy is slowly changing, it could cause tiny, predictable variations in the fundamental constants of nature, such as the fine structure constant which governs the strength of electromagnetic interactions. An atomic clock works by measuring the unwavering frequency of light emitted when an electron jumps between energy levels in an atom. If that fine structure constant were subtly shifting over time due to a changing dark energy field, the clock's tick would slowly drift. By comparing multiple ultra-precise clocks that rely on different atoms over months or years, physicists hope to catch this cosmic drift in action, witnessing the direct fingerprint of an evolving dark energy field right here on Earth. Another daring line of attack seeks to measure the force of dark energy itself in a vacuum chamber. While the energy density of the vacuum is incredibly small, it is not zero. In principle, this should exert a tiny, constant pressure. The Casimir effect offers a glimpse of this. When two perfectly smooth, neutral metal plates are placed incredibly close together in a vacuum, they are pushed toward each other. This happens because the quantum fluctuations of the vacuum between the plates are restricted, creating a pressure difference. Some theorists suggest that a precise enough measurement of this effect, or related quantum vacuum phenomena, could reveal a contribution from the dark energy background. These experiments operate at the very edge of our technological capabilities, measuring forces smaller than the weight of a single virus. The quest to directly detect dark energy is a testament to human ingenuity, a struggle to perceive a force that defines the cosmos by looking for its faintest whisper in the quietest places we can create. Success would transform dark energy from a cosmic inference into a tangible part of our physical reality, a component we can finally hold, in a sense, in the palm of our hand. The ghostly nature of dark energy draws us back to its most promising and most problematic theoretical source. Deep within the fabric of space at the quantum level, nothing is ever truly still. Empty space is a seething ocean of activity, where virtual particle pairs constantly flicker into existence and then annihilate each other almost instantly. This ceaseless activity, known as quantum fluctuations, endows the vacuum with a fundamental energy, a hum that should be present everywhere. This is zero-point energy, and it seems like the perfect candidate for the cosmological constant. It is a natural, intrinsic energy of space itself, a repulsive force baked into the very laws of quantum mechanics. The math seems to line up beautifully until you actually do the calculation. When physicists sum up all the potential energy from every possible quantum fluctuation in the vacuum, the result is a number of such staggering magnitude it defies comprehension. This predicted vacuum energy should be so immensely powerful that it would have ripped the universe apart in the first fraction of a second of its existence. The cosmos we see, with its delicate galaxies and the possibility for life, would be utterly impossible. This is the heart of the cosmological constant problem in its rawest form. The theoretical prediction is wrong by a factor of 1 with 120 zeros after it. It is the most spectacular failure of a prediction in the history of science. How can the universe be so quiet and stable when our most fundamental theories scream that it should be in a state of violent, explosive chaos? This forces us to consider more exotic quantum possibilities. One fascinating idea involves the Casimir effect, but on a cosmic scale. In a laboratory, the Casimir effect is observed when two uncharged metal plates placed incredibly close together in a vacuum are pushed toward each other. This happens because the plates restrict the types of quantum fluctuations that can exist between them, creating a pressure difference. Now, imagine this same principle applied to the entire universe. What if the structure of space itself, its topology or the presence of hidden extra dimensions, acts like a cosmic Casimir plate, somehow cancelling out or suppressing the titanic zero-point energy, leaving behind only the tiny, residual effect we call dark energy? Perhaps the vacuum energy is real and colossal, but most of it is trapped or confined in a way we cannot yet perceive, with only a minuscule leak into our four-dimensional reality. This would mean the dark energy we measure is just the faint echo of a much vaster quantum reality happening all around us. Exploring these possibilities takes us to the very edge of theoretical physics, where the smooth fabric of general relativity collides with the chaotic jitter of the quantum world. The solution to the dark energy puzzle may require us to find the missing key that finally unites these two great pillars of physics, revealing why the hum of nothing is so much quieter than it has any right to be. This very act of observation forces us to confront a deeply controversial explanation for dark energy's puzzling value. The anthropic principle argues that the constants of nature, including the strength of dark energy, are not random. They appear finely tuned because they must be compatible with our own existence. We could not possibly find ourselves in a universe where dark energy is too strong, because such a cosmos would be sterile and empty. If dark energy were just a few hundred times more powerful than what we measure, its repulsive push would have overwhelmed gravity in the universe's infancy. Proto-galaxies would have been blown apart before they could ever collapse, scattering the primordial gas needed to form stars and planets. No stars, no planets, no chemistry, and certainly no astronomers to wonder about it all. Conversely, if dark energy was significantly weaker or even attractive, the universe might have collapsed back on itself in a big crunch long before life had a chance to emerge. Our presence here, looking out at the cosmos, automatically selects for a universe where the dark energy is just weak enough to allow for structure, but just strong enough to create the vast, expanding stage we see today. This line of reasoning finds its most profound expression in the concept of the multiverse. Imagine not one universe, but a boundless, bubbling froth of universes, each with its own unique, random set of physical laws and constants. In this infinite landscape, most universes are stillborn or barren. Some have gravity that is too weak to form stars, others have nuclear forces too strong to allow for stable atoms. In this vast cosmic lottery, a tiny, almost infinitesimal fraction of universes will, by pure chance, have the perfect combination of constants for life. We do not live in a special universe, we simply live in one of the very few universes that can support life. The value of dark energy is not a fundamental law waiting to be derived from a grand equation. It is a cosmic coincidence we are forced to observe. This idea is as unsettling as it is compelling. It shifts the goalposts of science from explaining why the constants have the values they do, to simply accepting that we live in a place where they can. For some, this is a philosophical cop-out, a retreat from the dream of a single, elegant theory of everything. For others, it is the ultimate expression of our place in the cosmos, a humbling reminder that the universe was not made for us. We are just lucky enough to find ourselves in a corner of it that allows us to be. The debate rages on, a fundamental clash between the search for a unique, necessary cosmos and the haunting possibility that we are just one outcome in an endless sea of random possibilities. This fleeting early energy could have been the universe's first ghost, a temporary push that vanished almost as quickly as it appeared. Early dark energy is the radical proposal that a form of dark energy, distinct from what we see today, briefly flared into existence during the cosmos's first few 100,000 years. At this time, the universe was a seething, opaque plasma, too hot for atoms to form. Within this hot soup, pressure waves raced through the material, creating ripples like sound waves in a cosmic sea. The distance these sound waves could travel before the universe cooled enough for atoms to form and the plasma cleared, a moment called recombination, is frozen in time. We see its imprint as a specific scale in the cosmic microwave background, a cosmic ruler known as the sound horizon. This ruler is what we use to measure the geometry and expansion history of the early universe. Now, here is where early dark energy performs its magic. If this transient energy field was active just before recombination, it would have provided a short, extra burst of acceleration. Think of it as a sudden gust of wind that blows across a pond just before the surface freezes. This gust would have stretched the fabric of space a little more, affecting how far those primordial sound waves could travel. It would have reduced the size of the sound horizon. When we look at the cosmic microwave background today, we are using that smaller, altered ruler to take our measurements. This is the key to potentially solving the Hubble tension. Our current models, which assume no early dark energy, take the small sound horizon we observe and calculate a slower expansion rate for the universe today. But if that ruler was artificially shortened by an early burst of dark energy, then our calculation is based on a flawed assumption. When we correct for this, the predicted expansion rate for the modern universe jumps up, potentially aligning perfectly with what we actually measure from supernovas and other local sources. The ghost of this early push resolves the discrepancy by changing our understanding of the starting conditions. The evidence for this is not yet solid, but the hunt is on for its unique signature. The most promising place to look is in the polarization of the cosmic microwave background. When the universe became transparent during recombination, the light didn't just stream out in temperature, it also carried a specific direction or polarization, imprinted by the last scattering with electrons. Early dark energy would have subtly altered the pattern of this polarization in a specific way. Future observatories like the Simons Observatory and the Next Generation CMB-S4 project are being designed with the exquisite sensitivity needed to read this faint, ancient script. They will scour the microwave sky for the telltale swirls and patterns that scream of a brief, primordial acceleration. Finding this signal would do more than just solve a measurement problem. It would reveal that dark energy is not a single, monolithic force, but a phenomenon that can manifest in different forms across cosmic history. Our universe may have experienced multiple dark energy eras, a first brief push in its infancy and a second, longer one governing its old age. This would transform our cosmic story, suggesting that the acceleration we see today is not a unique event, but part of a deeper, more dynamic rhythm written into the laws of physics themselves. But even the most pristine data can hide a terrifying pattern. Deep within the glow of the cosmic microwave background, the universe's baby picture, astronomers have stumbled upon a series of strange anomalies that together have earned a chilling name, the axis of evil. This is not a single feature, but a collection of oddities that seem to align with each other, and more shockingly, with the plane of our own solar system. It is as if the entire cosmos has a faint, ghostly fingerprint, and our local neighborhood is pointing directly toward it. The most prominent of these anomalies is a strange alignment in the largest waves of temperature fluctuation across the sky. These primordial ripples should be oriented randomly, pointing in every direction with no preferred axis. Instead, they show a subtle but statistically significant preference for aligning along a specific plane that correlates with our solar system's ecliptic. Another piece of the puzzle is the mysterious cold spot, a vast, unusually cold region in the cosmic background that also seems linked to this preferred direction. These correlations defy the most sacred rule in cosmology, the cosmological principle. This principle states that the universe on large scales is homogeneous and isotropic. It should look the same in every direction and have no special center or preferred axis. The universe should not care about the orientation of our little solar system. The existence of the axis of evil suggests it might, so what could this mean? The most conservative explanation is that this is a colossal systematic error. Perhaps some unknown contamination from our own galaxy, or even from the solar system itself, is subtly imprinting this pattern on the data, fooling us into seeing a cosmic mystery where none exists. Alternatively, it could simply be a statistical fluke. When you look at enough data, sometimes strange patterns emerge purely by chance, but the possibility that refuses to go away is the most profound one. What if the axis of evil is real? What if it is a sign that the dark energy driving cosmic acceleration is not perfectly uniform? We assume dark energy pushes with equal strength in all directions, but what if it has a preferred direction? This would mean the expansion of the universe is anisotropic, stretching faster in some directions than in others. Our entire cosmic neighborhood, including the Milky Way, could be drifting along a subtle gradient in this dark energy field, a cosmic slope that leaves its imprint on the oldest light we can see. This would not just be a new property of dark energy, it would be a revolution in our understanding of reality, forcing us to abandon the foundational idea of a perfectly uniform cosmos. The hunt is now on to confirm or debunk this eerie alignment, a search that will either restore order to the universe or reveal it to be fundamentally lopsided, guided by a hidden axis we are only just beginning to see. Perhaps the most radical solution to the cosmological constant problem is that our perception of reality is a magnificent illusion. The holographic principle, born from the study of black holes, proposes that our three-dimensional universe of depth, width, and height is actually a projection of information encoded on a distant two-dimensional surface. Think of the world around you not as a solid, independent reality, but as a cosmic hologram. All the information needed to describe every star, every planet, and every one of us could be painted on the outer boundary of the observable universe like a gigantic spherical DVD. What we experience as a rich, three-dimensional world is just an incredibly detailed reconstruction from that data. This is not science fiction, but a serious consequence of uniting quantum mechanics with gravity. When applied to the entire cosmos, this idea offers a breathtakingly elegant explanation for dark energy. The energy of the vacuum, the source of cosmic acceleration, may not be a mysterious substance we need to add to our equations. Instead, it could be a natural consequence of the limited number of fundamental pixels or bits of information that our universe can possibly contain. In a three-dimensional world, our theories predict an infinite amount of vacuum energy, leading to that catastrophic miscalculation. But in a holographic universe, the true number of degrees of freedom, the amount of information needed to describe everything, is finite and is determined by the area of the cosmic boundary, not the volume within it. This fundamental limit on information acts like a cosmic regulator. It prevents the vacuum energy from reaching the unimaginably high values our standard math predicts, suppressing it by precisely the colossal factor of 1 followed by 120 zeros that we need. The tiny residual value that remains after this cosmic censorship is exactly the dark energy we observe. In this view, the acceleration of the universe is not driven by a phantom force, but is a direct reflection of the information content of reality. The expansion is what happens when the cosmic hard drive has a specific, finite capacity. This provides a first principles derivation for the value of dark energy, something that has eluded physicists for decades. The holographic principle turns the worst prediction in physics into a potential triumph, suggesting that the answer to the mystery of dark energy was never hidden in the volume of space, but on its surface all along. The universe is not telling us about a new energy, it is whispering that we have been counting its fundamental ingredients in the wrong way. Could it be that the ultimate nature of reality is not three-dimensional, but that depth itself is a beautiful, persistent mirage projected from the edges of space and time? The race to unmask dark energy is accelerating, powered by a new generation of cosmic observatories designed as dedicated detectives for this invisible force. These are not general-purpose telescopes, but highly specialized instruments built with one primary goal: to measure the expansion history and growth of cosmic structure with a precision we can barely conceive of today. Leading this charge are three monumental projects: the European Space Agency's Euclid spacecraft, the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, and NASA's Nancy Grace Roman Space Telescope. Each will attack the mystery from a different angle, creating a multi-pronged assault on the unknown. Euclid, already in space, is a surveyor of the extragalactic sky. It will map the three-dimensional distribution of billions of galaxies across 10 billion years of cosmic history. Its primary tool is weak gravitational lensing, the subtle warping of light from distant galaxies as it passes through the gravitational fields of dark matter. By measuring these tiny distortions on an immense scale, Euclid will trace the distribution of all matter, both light and dark, and track how the cosmic web has grown over time. Any suppression or enhancement of this growth, caused by the repulsive push of dark energy or a modification of gravity, will be imprinted in this detailed map. The Vera-C, Rubin Observatory, with its colossal 3.2 gigapixel camera, will conduct an unprecedented 10-year movie of the sky called the Legacy Survey of Space and Time. From a mountaintop in Chile, it will scan the entire visible sky every few nights, discovering billions of new galaxies and monitoring millions of transient events. Its immense power lies in statistics. It will find and measure so many Type 1 supernovas that the curve of cosmic expansion can be drawn with razor-thin error bars. Simultaneously, it will use another cosmic ruler, Baryon acoustic oscillations. These are the fossilized imprints of those primordial sound waves from the early universe, providing a standard measuring stick etched across the cosmos. By tracking how the apparent size of this ruler changes across different cosmic epochs, astronomers can reconstruct the expansion history with phenomenal accuracy. Finally, the Nancy Grace Roman Space Telescope will combine the wide-field survey power of Rubin with the razor-sharp vision of space-based observation, free from the blurring of Earth's atmosphere. Roman will perform its own massive galactic survey, using both weak lensing and Baryon acoustic oscillations with a clarity that is simply impossible from the ground. Its unique capability lies in its high-resolution near-infrared vision, allowing it to peer deep into the cosmic dawn, to a time just a few billion years after the Big Bang, when dark energy was first beginning to influence the cosmos. This is the critical era where we expect to see the handover from a matter-dominated universe to a dark energy-dominated one. Together, this trio will not just measure the equation of state of dark energy, they will watch for any sign that it changes over time. They will determine if the growth of structure matches the predictions of general relativity or if it hints at modified gravity. They will search for the coupling between dark energy and dark matter by counting galaxy clusters across cosmic time. This is not merely an incremental improvement, it is a leap into a new era of precision cosmology. The data from these observatories will contain the answers to our most profound questions. Is dark energy a simple constant, a dynamic field, or a sign that our gravity is broken? The next decade of observation promises to turn our philosophical debates into empirical facts, finally bringing the dominant force in the universe into sharp, undeniable focus. This cosmic tug-of-war has left its mark on the very architecture of the universe. For nearly 9 billion years, gravity was the undisputed master of the cosmos, tirelessly pulling matter together into an intricate web of filaments and clusters. Vast rivers of gas and dark matter flowed along these cosmic highways, feeding the growth of galaxies and the immense superclusters they call home. Then, around 5 billion years ago, the balance of power shifted. Dark energy's influence grew from a whisper to a dominant shout, and the era of unfettered structure building came to an end. Think of dark energy as a cosmic headwind, a pervasive resistance against gravity's pull. It did not destroy the structures that had already formed, but it began to stifle the birth of new ones on the grandest scales. The flow of material along the cosmic web was throttled. Galaxy clusters, the largest gravitationally bound structures in the universe, found their growth stunted. They could no longer pull in as much new material from their surroundings, freezing them in a state that reflects the moment dark energy took control. The universe's large-scale structure is therefore a fossil record of this pivotal transition. The cosmic web we map today is not a snapshot of ongoing construction, but a relic of a more dynamic past, a universe caught between its gravitational history and its expansive future. If dark energy were significantly stronger than we observe, this fossil record would be barren. A more powerful repulsive force would have overwhelmed gravity much earlier, perhaps when the universe was only a fraction of its current age. The primordial gas would have been blown apart before it could ever collapse into substantial galaxies. The cosmos would be a lonely, sparse sea of isolated dwarf galaxies, with no grand clusters or superclusters to speak of. There would be no cosmic web, only a faint, diffuse mist of stars. Conversely, if dark energy were much weaker or entirely absent, gravity would still reign supreme. The universe would be a far denser, more crowded place. The cosmic web would continue to condense, pulling vast superclusters into ever tighter knots. Galaxies would merge more frequently, and the universe might already be showing signs of an eventual collapse, a dramatic reversal of the expansion. The delicate balance we observe is what allowed for both the formation of rich structures like our own Milky Way and the vast navigable voids between them. Every filament of the cosmic web, every immense cluster of galaxies, tells a story of that critical moment 5 billion years ago when the universe's expansion began to accelerate, quietly putting a ceiling on the ambitions of gravity itself. This rolling field of quintessence offers a compelling escape from the stark predictions of a simple cosmological constant. Instead of a fixed, immutable energy baked into space, quintessence is a dynamic entity, a cosmic scalar field that permeates every corner of the universe. Think of it not as a static number, but as a ball resting high up on a vast, gently sloping hill of potential energy. In the early universe, this ball was perched near the top, its high potential energy contributing a powerful repulsive force that could have influenced the cosmos's first moments. As the universe expands and ages, the ball slowly, almost imperceptibly, rolls down this hill. As it rolls, its potential energy decreases, and so too does the strength of the repulsive force it exerts. This slow roll is the heart of the model, transforming dark energy from a perpetual constant into an evolving component of the cosmos, one whose influence can wax and wane over billions of years. This dynamic nature leaves a distinct fingerprint that astronomers are desperate to find, a clear deviation from the simplest model. For a pure cosmological constant, the equation of state parameter is forever locked at exactly -1. But for a quintessence field, this number is not a constant. It is a moving target. As the field rolls down its potential, its equation of state begins to deviate from -1. Typically becoming slightly less negative over time. This tiny drift, if we can measure it, would be the smoking gun for a universe governed by a dynamic dark energy, shattering the simplistic model we have relied on for decades. Furthermore, unlike the passive vacuum energy of a cosmological constant, a quintessence field could interact with matter, particularly dark matter, in subtle ways. This interaction could leave a second fingerprint on the growth of cosmic structure. A rolling quintessence field would not just change the expansion history, it could also siphon energy away from or deposit it into the dark matter that sculpts galaxies and clusters. This would alter the rate at which the largest structures in the universe form, suppressing or enhancing their growth in a way that a simple cosmological constant cannot replicate. These two signatures, a drifting equation of state and a modified growth of structure, make quintessence the primary theoretical target for the next generation of observatories. The Euclid, Rubin, and Roman telescopes are not just measuring a single number, they are watching for this cosmic drift, hunting for any sign that the ball has begun its slow roll down the hill. Finding evidence for quintessence would be a revolution, revealing that the force dominating our universe is not a feature of empty space, but a new, fundamental ingredient in the cosmic recipe, one that is still evolving and whose ultimate fate remains an open, thrilling question. This negative pressure is the true engine of cosmic acceleration, a concept that bends our everyday intuition to its breaking point. We are used to pressure being a positive, pushing force. The air in a tire pushes outward, keeping it firm. The water at the bottom of the ocean pushes inward with crushing weight. But in the strange world of general relativity, pressure is not just a force, it is a source of gravity. And when that pressure is profoundly negative, it generates a gravitational effect that is not an attraction, but a repulsion. To grasp this, picture a perfectly elastic rubber sheet representing the fabric of spacetime. Now imagine you are trying to stretch that sheet in all directions at once. This act of stretching requires you to pull, to exert a negative pressure on the sheet. In Einstein's universe, this very act of pulling on the fabric of space itself contributes to gravity in a bizarre and counterintuitive way. It creates a sort of tension that, according to his equations, makes the fabric want to stretch even more. This is not anti-gravity in the science fiction sense, a magical force that repels matter. It is a direct consequence of how all forms of energy and pressure warp the geometry of the cosmos. In Einstein's field equations, the source of gravity is not just mass or energy density, but also pressure and even shear stresses. They are all woven together into a single quantity called the stress-energy tensor. For most of the things we encounter, like planets, people, or radiation, the pressure component is either positive or so tiny that its gravitational effect is completely negligible compared to its energy density. Its contribution simply adds to the attractive pull of gravity, but for dark energy, the situation is flipped. Its energy density is incredibly small, but its pressure is not just negative, it is strongly negative. In fact, for the simplest form of dark energy, the pressure is exactly equal to the negative of its energy density. This is the magical value that makes the repulsive effect kick in. When you plug this relationship into Einstein's equations, the negative pressure term does not add to the attractive gravity, it subtracts from it. And since the pressure is so strongly negative, it overpowers the energy density's weak attraction and flips the sign. The result is a net repulsive gravity. Think of a sealed container filled with a substance that has this strong negative pressure. If you tried to add more of this substance, the container would actively resist being filled, pushing back as if the very act of compression were anathema to its nature. On a cosmic scale, this repulsive gravity does not push galaxies apart like a wind. Instead, it causes new space to form between them. The universe is not flying apart into a pre-existing void, it is creating more room, stretching the very stage on which galaxies sit. Every cubic centimeter of empty space possesses this tiny, negative pressure, and the collective effect of all that nothing, stretched across the vastness of the cosmos, is a repulsive force so powerful it dominates the fate of everything. This is the profound revelation of Einstein's genius, that the nothingness of the vacuum is not passive, but is dynamically woven into the gravitational fabric of reality, and its inherent tension is what is relentlessly accelerating the expansion of our universe. This ghostly repulsive gravity is not the only invisible actor on the cosmic stage. For decades, we have known about another set of spectral particles that barely interact with normal matter, streaming through our bodies and our planet by the trillions every second. These are neutrinos, and their tiny, non-zero masses are now adding a new layer of intrigue to the dark energy saga. While neutrinos are incredibly light, their sheer numbers mean they contribute to the overall cosmic energy budget, and their unique behavior has a subtle but measurable impact on how the universe's large-scale structure formed. Because neutrinos travel at near light speed for much of cosmic history, they act like a kind of cosmic pressure, smoothing out the densest knots of matter and slightly suppressing the growth of the very largest galaxy clusters. This leaves a faint imprint on the cosmic web, a signature that the next generation of telescopes is poised to measure with incredible precision. But the connection could run far deeper than a simple background effect. Some of the most speculative and fascinating theories in physics propose a direct link between these elusive particles and the force driving cosmic acceleration. Imagine a model where the mass of a neutrino is not a fixed number, but a value that changes over time, tied directly to the evolution of a quintessence field. In this mass-varying neutrino scenario, the dark energy field that fills the cosmos also dictates the mass of the neutrino. As the quintessence field rolls down its potential hill, slowly changing the strength of dark energy, it simultaneously adjusts the mass of every neutrino in the universe. This creates a profound feedback loop. The neutrinos, in turn, influence how the quintessence field evolves, their changing masses providing a kind of cosmic friction or catalyst for the field's motion. This intimate coupling between the universe's largest scale force and one of its most fundamental particles offers a potential bridge between particle physics and cosmology. It suggests that the answer to the dark energy puzzle might not be found in the emptiness of space alone, but in the hidden properties of particles that have been flowing through the cosmos since its first second. Detecting such a link would require catching neutrinos in the act of changing, a monumental challenge that pushes the limits of our experimental ingenuity. Yet the mere possibility reminds us that the universe's greatest mysteries are likely intertwined, and that the key to understanding the void may lie in the subtle dance of its most ghostly inhabitants. Deep within the inescapable gravity of a black hole, a battle rages over the nature of reality itself. This is the black hole information paradox, a conflict between general relativity and quantum mechanics that has divided physicists for decades. The problem is deceptively simple. According to Einstein, a black hole is defined only by its mass, spin, and charge. If you throw a grand piano, a collection of love letters, or a box of assorted feathers into a black hole, the black hole would not care. It would simply get a little more massive, and according to classical physics, the information about what fell in would be lost forever. But quantum mechanics has a sacred, unbreakable rule. Information cannot be destroyed. It can be scrambled, hidden, or encoded, but it must, in principle, be recoverable. So, when a black hole eventually evaporates through Hawking radiation, what happens to the information that defined the piano, the letters, and the feathers? Does it vanish, violating quantum law, or is it somehow encoded in the radiation, a possibility that challenges our understanding of spacetime itself? This paradox pits our two most successful theories against each other in a fight for the soul of physics. Now, a startling new idea is emerging from the cosmic depths, suggesting the key to this 50-year-old puzzle might be tied directly to the dark energy accelerating our entire universe. The connection hinges on the concept of entropy, which is essentially a measure of disorder or hidden information. Every system has entropy, and black holes have a tremendous amount of it, proportional to the area of their event horizon. But black holes are not the only horizons in the cosmos. Our accelerating universe has one too. It is called the cosmological event horizon. This is the ultimate prison wall, a boundary beyond which no light signal we send today will ever reach, thanks to the relentless stretch of dark energy. Just like a black hole's horizon, this cosmic boundary has a temperature and, most importantly, a colossal entropy. This is where the threads entwine. Some physicists are now proposing that the fundamental resolution to the information paradox lies not within the black hole itself, but in the way its information is connected to the entropy of this cosmic horizon. In this radical view, the information swallowed by a black hole is not lost, but is somehow delocalized and imprinted onto the fabric of the cosmological horizon, the largest structure in the universe. The dark energy that creates this horizon acts as a cosmic hard drive with an unimaginably vast capacity to store quantum information. This implies a breathtaking unity. The fate of a single bit of information falling into a black hole, the smallest of quantum mysteries, is irrevocably tied to the ultimate fate of the entire cosmos, driven by its dark energy. The physics of the infinitesimally small is speaking the same language as the physics of the impossibly large. If this speculative link holds, it would mean that dark energy is not just a lonely force pushing galaxies apart. It is an active participant in the most fundamental quantum processes, providing the necessary canvas upon which the universe preserves its memory. Solving the black hole information paradox might require us to first understand the dark energy that defines our cosmic horizon, forever linking the destiny of the smallest particles to the grandest stage of all. One of the most stubborn and chilling puzzles in the cosmic background radiation is a place known simply as the cold spot. This is not a minor temperature dip, but a vast, circular region of the sky, far larger than our entire Milky Way galaxy, that is significantly and mysteriously colder than the surrounding cosmic glow. According to our standard models of cosmology, a feature this large and this cold should be incredibly rare, a statistical fluke with odds of less than 1 in a million. Its very existence challenges the smooth, uniform picture of the early universe we thought we understood. The most conservative explanation astronomers have proposed is a cosmic ghost town, a supervoid. This would be a truly colossal bubble in space, a region of staggering emptiness spanning hundreds of millions of light years where the density of galaxies and matter is far lower than the cosmic average. If we were sitting on the edge of or inside such a void, the explanation goes, the cold spot could be a trick of cosmic energetics. As light from the cosmic microwave background travels through an underdense region, it must climb out of a gravitational well that is shallower than average. This process, called the integrated Sachs-Wolf effect, causes the light to lose a tiny amount of energy, making it appear slightly colder when it finally reaches us. For the cold spot, the problem is one of scale. To produce the observed temperature drop, this supervoid would need to be of such an immense size and emptiness that it pushes the limits of what our models of structure formation allow. Dark energy plays a crucial role here, as its repulsive push over the last 5 billion years would have actively suppressed the growth of new structures, making it even harder for such a gigantic void to naturally form. If a supervoid is the culprit, it would mean dark energy helped create the very emptiness that now presents us with this profound anomaly. The alternative is far more radical. What if the cold spot is not a void, but a cosmic bruise? Some theorists suggest it could be the imprint of a collision between our universe and another bubble universe in the vast multiverse. In this breathtaking scenario, the cosmic background radiation carries the scar of a primordial impact, a place where the fabric of our reality briefly interacted with another, entirely different cosmos. The energy of that collision would have left a distinct cold signature on the sky, a permanent mark of a world beyond our own. This idea forces us to consider dark energy in a completely new light. In many multiverse theories, the value of dark energy in each bubble universe is random. Our universe has a specific, small value that allows for galaxies and life. A collision with another bubble could imply that these universes are not entirely separate, and that their fundamental properties, including their dark energy, can interact. The cold spot could be direct evidence that our cosmic horizon is not the final frontier, and that the force accelerating our expansion is just one possibility in an infinite tapestry of realities. The search for the truth is ongoing. Astronomers are meticulously mapping the galaxy distribution in the direction of the cold spot, looking for the telltale absence of matter that would confirm the supervoid hypothesis. So far, the evidence is ambiguous, with some surveys finding underdensities, but none large enough to fully explain the profound cold. The void explanation remains just within the realm of possibility, while the multiverse collision sits at the edge of scientific speculation. Yet the cold spot persists, a cold eye in the sky staring back at us. It asks a simple, terrifying question. Are we looking at a rare but natural cosmic structure, or is this the first tangible evidence of a reality beyond our own, a place where the rules of our universe were once bent by a touch from another? Our relentless search for answers eventually leads us to a quiet, humbling space beyond equations and data. The discovery of dark energy is not just a scientific revolution. It is a profound philosophical event, forcing us to reconsider our very place in the grand scheme of existence. For centuries, we saw the cosmos as a stable, perhaps even welcoming arena. Now we know it is dominated by a force whose ultimate purpose seems to be separation and isolation. This reality carries a deep, inherent cosmic pessimism. The vision of a heat-death future, a cold, dark, and eternal emptiness where all lights go out and all stories are forgotten, can feel like the ultimate negation of meaning. It suggests a universe that is not just indifferent to life, but one that is actively constructing a prison of infinite solitude, pushing every island of matter beyond the edge of forever. Yet there is a countervailing awe. The sheer fact that we, tiny beings on a speck of dust, can perceive this vast, dark destiny is itself a staggering triumph of consciousness. We are the universe awakening to its own strange and magnificent story, even if that story ends in silence. This knowledge challenges two foundational principles that have guided science for generations. The first is naturalness, the elegant expectation that the fundamental constants of nature should be of a reasonable, explainable magnitude, not absurdly fine-tuned. Dark energy shatters this principle. Its incredibly small, yet non-zero value seems unnaturally fine-tuned for life, a fact that either points toward a multiverse or a cosmos with a purpose we cannot yet grasp. The second challenged principle is testability. The best ideas in science can be proven wrong, but when our leading theories predict a vacuum energy wrong by 120 orders of magnitude, and the most popular alternative explanation is an infinite multiverse we can never observe, we are forced to ask if we are reaching the limits of what is knowable. Does dark energy mark a boundary for human inquiry, or is it simply the next great frontier, daring us to develop new tools not just of observation but of thought itself? In the face of this immense, accelerating darkness, our quest for understanding becomes its own kind of light, a defiant act of finding purpose not in the universe's ultimate fate, but in the profound act of seeking to comprehend it. Yet after all these mysteries, we must confront one final, radical possibility. What if the accelerating expansion is not real at all? Could every measurement, every careful observation be pointing toward a grand cosmic illusion? The evidence for dark energy rests on three mighty pillars, but each one relies on our ability to correctly interpret the light reaching us from across the cosmos. The first pillar is the observation of distant supernovas. We see these exploding stars as fainter than they should be if the universe were coasting or slowing down. Their dimness suggests they are farther away than expected, a key sign of accelerating expansion. But what if our understanding of these supernovas is flawed? Perhaps they were intrinsically dimmer in the past, or maybe interstellar dust we have not accounted for is subtly dimming their light across billions of light years, fooling us into seeing acceleration where there is none. The second pillar is the cosmic microwave background. The precise patterns in this ancient light allow us to calculate the universe's geometry and content, predicting the acceleration we see today. This model is incredibly successful, but it is a chain of inference. If our interpretation of the physics of the early plasma is even slightly incorrect, the entire chain could break, leading us to a false conclusion about the need for dark energy. The third pillar is baryon acoustic oscillations, the frozen sound waves in the distribution of galaxies. This cosmic ruler seems to confirm the acceleration story, but it too depends on a complex model of how structure forms. A subtle, unknown effect in how galaxies trace the underlying dark matter could warp this ruler, making the universe appear to be stretching faster than it truly is. Could there be a single, common thread of error running through all these independent methods? It seems unlikely, but not impossible. Perhaps our most fundamental tools are flawed. Our entire cosmic distance ladder, the step-by-step method we use to measure the vast scales of the universe, is built on a series of assumptions. What if our standard candles are not so standard? What if our understanding of how light redshifts over cosmic distances is incomplete? The redshift of a galaxy is not just a measure of velocity, it is a measure of how much the universe has stretched while the light was in transit. This is a cornerstone of modern cosmology, but could we be misinterpreting this cosmic stretch? If the nature of light itself or the properties of the vacuum were different in the past, it could mimic the effects of acceleration without any dark energy at all. This is not a call to abandon our methods, but to refine them with ruthless skepticism. The history of science is filled with brilliant ideas that were later overturned. The geocentric universe, the luminiferous ether, the steady-state theory, all were once leading paradigms that collapsed under the weight of new evidence. Dark energy could be the next, or it could be one of the greatest discoveries of all time. This final mystery is a reminder that the scientific process is not about finding final answers, but about asking better and better questions. The true nature of dark energy, or its stunning absence, awaits the next great leap in our perspective, a leap that may force us to rewrite not just our cosmic history, but the very laws we use to read it. From the staggering failure of the cosmological constant prediction to the haunting possibility of a phantom-driven Big Rip, these 25 mysteries paint a portrait of a universe far stranger than we ever dreamed. We are surrounded by a force that makes up most of reality, yet we cannot see it, touch it, or even begin to explain its profound weakness. Our most cherished theories are at war with each other, our most precise measurements are in tension, and our ultimate fate hangs in the balance between eternal silence, violent dissolution, or cyclical rebirth. The journey through these puzzles reveals a cosmos that is not a static backdrop, but a dynamic, evolving entity filled with phantom energies, cosmic voids, and the unsettling possibility that our reality is a holographic projection. We have confronted the ghostly influence of dark energy on the growth of galaxies, wrestled with the philosophical implications of the anthropic principle, and even considered the chilling prospect that the acceleration itself is a grand illusion. Every answer we have found only leads to deeper, more fundamental questions. Unraveling this cosmic puzzle will not be a simple matter of filling in a blank. It demands a revolution in our understanding of physics as profound as the shifts brought by Einstein's relativity and the birth of quantum mechanics. It will require us to tear down the walls between the infinitely large and the infinitesimally small, forging a new theory of quantum gravity that can finally explain the dark heart of our universe. This is not the end of the story, but the very beginning of a new chapter in human discovery. The next decade of observation with telescopes like Euclid, Rubin, and Roman will deliver a flood of data that could crack these mysteries wide open. Stay curious, follow these incredible missions, and look to the night sky with a sense of wonder. The greatest revelations are still to come. Now we want to hear from you. Which of these 25 mysteries keeps you awake at night, and what do you think dark energy truly is? Share your thoughts and your favorite cosmic puzzle in the comments below.